we've explored translating decimal integers into binary integers. The computer can store binary integers. That's just a sequence of ones and zeros, sequence of bits. So it seems like we know how int variable types are stored. What about floating points? What about 27.2? How do we do that? And you don't need to know the internals of this, but there are a couple of implications that can pop out and drive you very crazy in debugging a code if you don't at least understand the fundamentals of how these different types of numbers are stored. In the case of integers, there's clearly a largest integer that can be stored because 2 to the however many digits in your binary number is the number of states that you can represent. Maybe you use half of those to represent positive numbers and half of them to represent negative numbers. So there's a largest and smallest integer number that the computer can represent. In mathematics, integers go forever. The computer, not so much. And that one's pretty easy to understand. But let's look at floating point numbers, which have some similar restrictions. How would you store one? Well, and floating point just simply means a number like this. Any decimal number that's got something after the decimal point. Well, how we're going to represent this, in general, is an integer number times something to a power, like that. Well, that's good. We know how to store integer numbers. As a matter of fact, all of these are integer numbers. So it seems like what we need to do, and this is what's done, is we simply need to take these different parts and store them as different chunks, different slices of some string of zeros and ones. And that's exactly what we do. As a matter of fact, there's one more thing to keep track of, which is that. So there's a sign. Oh, that's only one digit, positive or negative. We call this the mantissa. And you probably don't need to know that, but whatever. It's nice to know. This is the base. That'll be built into the standard, and you'll use that. So it won't be stored, because every number will use the same thing. And then finally, that's the exponent. Obviously, you need to know that. That tells you where the decimal point goes. NT, sorry. And so how you store a floating point number is you just simply take a chunk of computer memory and you use different parts of it to store these different integer numbers. And there are different standards for this. You can use a different number of total digits. A typical one would be 0 to 31 bits, so a total of 32 bytes, sorry, binary digits in the total number. And the interesting thing about that is this is always going to be one of those digits, right? This is going to be 30 because you only need one binary number. But you can choose different bases, and you can choose different ratios of how much space you use for the mantissa and the exponent. The more mantissa you use, the more digits you get in your number. The more space you use for the exponent, the bigger and smaller numbers, 10 to the many or 10 to the minus many, that you can represent. So there's a bit of a trade there. And there are standards, and you don't have to worry about it. But it means, just like integers, there's a biggest, and in this case, smallest number, not smallest in terms of sign, but closest to 0, that you can represent. And in the case that I wrote there, if we make this the 23rd digit and that the 22nd, which is one of the common standards, the smallest number is 2 to the minus 126. 26. And that is around 10 to the minus 38 in rough numbers. Pretty darn small. And the largest pretty close, 10 to the positive 128. And there's just a little, dang it, I keep leaving the 2 out, 128. And that is about plus 10 to the 38 in round numbers. Which seems like, gee, that's a very tiny number and that's a very big number. But if you're doing some numerical calculation that's got the mass of a star or something in it, you might go over that. And if you go over that, a good compiler will say, you just overflowed your number system and I'm going to yell at you. And a not so good compiler would cause this number to roll around and perhaps become that number. You would just sort of wrap around in this circular system. And that's a bad thing. So if you hear about overflow errors and things like that and ways of breaking into computers, it's kind of related to this, that these numbers can only represent finite numbers of digits. So when we're doing practical programming assignments, we're going to talk about how these different numbers get used differently and the implications of working with them. Because you can see that they are a representation, a simulation of our normal continuous mathematical number line, but they're not a perfect simulation of that, and sometimes that matters.